The second session today on SIL selection using Excellencia. Just a couple of housekeeping notes here. Firstly, your microphones are muted so that we can cut back on any background noise, and there is a question and answer tab at the top. We will have time for questions at the end of the session. Furthermore, copies of these slides will be available in the next day or so, and we are also recording the session, so if anybody has to jump off, they can always come back and revisit this at a later date. So with that being said, I'm sorry, the sound for some reason remuted itself. I don't know. I will continue. As I was saying, for Exeter, the industry focus is based around automation, automotive, process and nuclear. We do support the manufacturers in terms of management support, development support, certification and tools to support those services. For system designers, we provide functional safety management, SIL verification and tools to support those services. For end users, we provide the SIL and device selection, SIL verification, as well as tools. We also provide hazard analysis, hazard and operability studies, as well as PHA facilitation. For engineering contractors, we provide tools and competence development through the CFSE. That's our Certified Functional Safety Expert program. And our primary lifecycle tool is called Excellencia. And the second part of this will be to look at the demonstration for Excellencia. So in terms of functional safety, the overall standard, the umbrella standard, is IEC 61508, which is a performance-based standard rather than a prescriptive standard. This means that the standard will tell you what needs to be done rather than how you need to do it. From that standard, there have been three main sector standards that have come out. One for the nuclear, which is 61513, one for the machinery sector, which is 62061, and the process industry sector 1, 61511, which is where we're going to focus today. In terms of the IEC 61511 standard. This is targeted at end users and integrators in the process industries. It covers the entire safety life cycle for an instrumented system. And there's effectively 3 phases for that. There's the first phase, which is where you do your risk analysis. The second phase, which is performance-based design. So from the first phase where you've done your risk analysis, you've done your assessments to see if you need some safety instrumented functions for your safety instrumented system, you then decide what level of risk reduction are you looking for, and you determine your SIL requirements. This gets put into your safety requirements specification document, which is then used as the basis for designing the actual safety instrumented system and the safety instrumented functions. And of course that's performance based. And then the final phase is the operations and maintenance, when the safety instrumented system is put into service and maintained through its life. Again, performance, not prescription. In terms of the end user applications, most end users are not typically certified, so they tend to use independent agencies to carry out independent functional safety assessments. And that's something that Exeter does a lot of. So if we look at the functional safety life cycle, you start off with your hazard identification, i.e. what can go wrong. So you do a process hazard analysis, you do a hazard and operability study to determine what are the potential hazards. And then you do your risk analysis and SIL selection. So basically, how bad can it be? What layers of protection do we need? What order of risk reduction are we looking for? And then, as I mentioned earlier, if we require a safety instrumented system with safety instrumented functions, then we need to document those requirements in a safety requirement specification. So that's what needs to be done. Then once you've done that, you have to verify that is the design that's come out going to meet the original requirement in terms of the safety integrity level. In other words, how reliable is it? And once you've done that, and you've made sure that the design meets the requirements, then during the normal life cycle of the system, there will be management of change, components will need to be replaced, so the safety instrumented functions need to be maintained in terms of their safety levels. So how to keep it safe? So if we look at risk analysis and SIL selection, this diagram is very interesting. As you'll see across the top, from left to right, the further right you go, the further the risk increases. So the target is to reduce that risk, and there's certain things that you can do initially to reduce that risk. You can look at the process. So in other words, if you're running a process that has hazardous materials, do those materials have to be stored on site? Do they need to be stored in different places? How would you minimize any potential for hazard to develop? The design of the site itself in terms of the plant, the way it's laid out, the basic process control system, the BPCS, and how that will mitigate against any of the potential hazards, the alarms that will be generated, any relief, and then finally the safety instrumented system. And you'll see there that we show in the middle the optimal risk reduction, which is as low as reasonably practical. And again, it all depends upon the company's risk tolerance, and is the reward worth the risk. As you can see, the mouse is thinking. So tolerable risk. Why do I need to specify my tolerable risk level? Well, if you don't do that, you won't know what your risk reduction should be. Because your risk reduction is your unmitigated risk over your target risk. And if you don't know what your target risk is going to be, then you won't be able to determine your risk reduction. So if you can't tolerate any risk, then your tolerable risk of 0 would lead to a required risk reduction of infinity, which basically says you should never build your plant. There is no such thing as 0 risk, as we all know. We take risks every day in driving to work, crossing the road, even climbing up the stairs and down again. So as we showed from the formula, if you don't have any tolerable risk, if it's 0, you're going to be an infinite risk reduction. So, mentioned the ALARF principle, as low as reasonably practical. If we look here, if we look at in the intolerable region, from a public point of view, that's one event or one death in every 10,000 years. Workers, it's 1 in every 1,000, and this is high risk and intolerable. If it's worth it, well, this is where we come into the as low as reasonably practical or tolerable region. And again, it really depends on the company's risk tolerance for risk, what they're prepared to accept and not accept. And you can see here this goes from 1 in 1,000 to 1 in a million. And as we said, driving a car is regarded as a tolerable risk. And then we accept it, the broadly acceptable region with negligible risk. And that is, as you can see from the little pictures there, being struck by lightning, being killed in a plane crash, and being bitten by a snake. So how do you assign a SIL? Well, the important thing, as we mentioned, is you've got to identify how much risk reduction is needed to attain a tolerable risk. This needs rigor, it needs flexibility, you need to consider all forms of harm, and you need to be consistent with the company and the society practice, and the form defines the SIL target selection method. You can use two types of method. Quantitative methods give specific numerical targets for risk and what we call risk reduction factor, and qualitative methods for grouping numerical targets into a broad category. So in other words, with a qualitative approach, you will get a SIL 1 or SIL 2 type answer, and SIL 1 would be a risk reduction between 10 to 100, and a SIL 2 would be between 100 and 1,000. The qualitative methods are useful for screening. You can do a first pass using qualitative methods, and then once you've screened, you can then use a more quantitative method to be able to define that more accurately. But in any event, you need to be consistent with the method or set of methods that you use. The common SIL selection methods that we use, and there's risk graph, hazard matrix or risk or hazard matrix, and frequency-based targets. You can use HAZOP and LOPA in relation to the risk criteria, and this allows you to be objective and to make uniform decisions about how much risk reduction is required in each case. The main thing is that you need to have your risk criteria defined, and that's usually what companies have as their tolerable risk criteria. A hazard matrix is fairly meaningless unless a LOPA was done to derive the numbers, but it's useful for screening purposes when severity is not high. In terms of Excellencia, risk graph, hazard matrix, and frequency-based targets are all methods that can be used with Excellencia. The tool that we use in Excellencia is called SILect. Here we're showing all the functions that Excellencia can provide, and we've highlighted here the SILect tool that is used for doing SIL selection. So if we look at the risk graph first of all, This selects categories for risk graph parameters. There's consequence parameters, likelihood parameters, and if you remember, risk is a measure of consequence and likelihood. So you're looking at occupancy, how often are people going to be there, can they avoid the hazard if it occurs, what is the demand rate or frequency, and in this case it's not a safety demand rate, it's frequency of occurrence, how often will this hazard occur without with any safety instrumented system. And then you follow the path determined by the selected parameter to identify the required SIL. And here you can see we have W1, 2 and 3. These are basically the rates, the demand rates. The consequences are over here, categories, and then you have the occupancy and the probability of avoidance or not. And you can see this from the next table. This is taken out of IEC 615.11.3, Annex D, and it describes the parameters, the consequence, which is the average number of fatalities likely to result from the hazard, and you can determine this by calculating the average numbers in the exposed area when the area is occupied. Occupancy, that's the probability that the exposed area is occupied, as we said earlier, and you can determine that by calculating the fraction of time the area is occupied. Probability of avoiding the hazard, that's the probability that the people will have the ability to avoid, to get out of the way. And then the demand rate, as we said, the number of times per year that the hazardous events will occur if there's no SIS. So, for example, here are the risk graph parameter values, and these would be defined per your company's risk criteria. So here we have W1, it's very low, less than once in 10 years, W2, 1 to 10 years, and W3 is less than a year. Then in each consequence category you have health and safety, which is personnel. So there's minor injury, severe injury, several deaths, or many deaths. Then impact on the environment, small uncontained release, moderate, large, etc. And assets, what is the impact on economics in terms of money. Then you can have additional parameters, which we've said already. There's occupancy is low or continuous or frequent, and then the ability to avoid the hazard, yes under certain circumstances, or no, it's almost impossible. These would be defined under your risk criteria. So if we look at an example, the SIF was identified during a HAZOP study. The safety department determined that probable loss of life is 0.9. The area is normally occupied. There is no possibility of avoiding the hazard, and the demand rate is 0.05 per year. So what is the SIL? Well, if we use the previous table, we can see that probability of loss of life is basically 1 death. So that would come under CB for severe injury or 1 death. The area is normally occupied, so that would be FB for frequently to continuously. There is no possibility of avoiding the hazard, so that would be a PB, almost impossible, and the demand rate is 0.05, so that's low, so that would be a W1. So if we put all that together, we can see that we'd be looking at a SIL1. Now you may be wondering what the A and the dotted lines are if you're not familiar with risk graph. The A basically means that there's no special safety systems. The B means that a single safety instrumented system is not sufficient. We're not showing any on this diagram. And the dotted lines means that there's actually no safety requirement. So in Excellencia, the risk graph looks more or less the same. And we will see this in a minute. Here we're looking at personnel, and here we have our frequencies, W1 through W3. Here we have our consequences. Here we have our occupancy, and then our ability to avoid or not. And this is the table that supports the risk graph. And you can define independent layers of protection. For a hazard matrix, again, as we said earlier, you really need LOPA to be done to derive the numbers. But here again we have the consequences and we have the likelihoods. So we categorize likelihood, we select the SIL from the matrix corresponding to the identified consequence and likelihood categories. So if we take a look here, the consequence considerations, you need to clearly identify the basis of categories. So you can include considerations for injury, loss of life, property damage, loss production, and environmental release. And those are typically what are taken into consideration. But, and the important thing to remember, is that the signing consequence category requires judgment and or further analysis. So again, quantitative calculation tools would be needed. If we look at an example again, let's say a SIF was identified during a HAZOP study. The hazard team determined that the dominant consequence is 1 death. The likelihood is once per 200 years. So what is the SIL? So again, looking at the demand rate, we're looking at 200 years, and that falls into D3, between 100 and 1,000. We're looking at a single fatality, so we will be looking at C3. So we've just looked at personnel using this example. So that means we'd be looking again at a SIL1. And you'd repeat the same for environment, and you'd repeat the same for asset. Bearing in mind that of these three, whichever has the higher SIL requirement becomes the dominant requirement. So in other words, if personnel was SIL1, environment was SIL1, but asset was coming out to be a SIL2, the SIF would have to be designed to meet SIL2. Looking in Excellencia, this is what the hazard matrix would look like, and here is the table that supports it. And again, we will look at these when we go into the Excellencia demo. So SIL selection using frequency-based targets. Fault tree analysis is another approach, using frequencies to select your SIL is another way of going. So you select the frequency target based on the consequence and assume that the consequence is constant. So you calculate your required risk reduction and you assign a SIL based on the required risk reductions. Fairly straightforward. So if we look at frequency-based targets, this is the frequency that's allowable for a hazardous event, and it depends upon the consequence. So here we're showing there are personnel, safety, fatalities, you've got minor, serious, severe, extensive, and catastrophic. And again, this would be derived from the company's overall risk criteria. These numbers would come from that. Then the required risk reduction is a function of the unmitigated accident frequency and the frequency target. So again, for our SIF, we will be looking at the frequency for the unmitigated event over the frequency for the target. So frequency-based targets, you select the SIL based on the required RRF. And you can see from the table, the risk reduction factors are converted there into SILs. The risk reduction factor target is converted based on this table, which comes from IEC 61511 or 61508. The selected SIL should give more risk reduction than required. That's important to understand because you normally always want to err on the conservative side when doing SIL selection. And you'll see that as we get into more detail, it's very important that when you are defining the SIL for the SIF, you make sure that there's no chance that the designer, who may not be and shouldn't be the same team, will be able to interpret it other than what you have specified. So again, if you're looking at quantitative, you will get order of magnitude. I'm sorry, qualitative, you will get order of magnitude SIL. If you're looking at quantitative, you can be much more accurate, and you can put in a safety margin. And we'll talk about that in a minute. So let's look at an example for a frequency-based target. Here we have an accident scenario that yielded a consequence of 0.21 probable loss of life and a likelihood of 1 in 57 incidents per year. So what should be the selected SIL? So the first thing you do is you look at the frequency category associated with a probable loss of life of 0.21, and it is severe. So that has an associated frequency target of 5 times 10 to the minus 4 per our table that we had defined a couple of slides back. So now we apply the target RI equation. So we put in what is our unmitigated event frequency against our target frequency, and as you can see, we come up with a risk reduction factor of 35.1. So normally that would give you a SIL1. But here we're saying SIL2 should be selected, or the risk reduction factor with appropriate safety margin must be part of the specification. Because a risk reduction factor of 35 puts it at the lower end of the SIL1, we may want to say, well, let's double it to make it give ourselves a safety margin, and say we want a SIF with a risk reduction factor of 70. If you want to be more conservative, you would just say we want a SIL2 SIF, which means that the designers would probably design the SIF to be at the lower end of the SIL2, which would be nearer a risk reduction of 100. So you can obviously add in safety margin, because it's very important that when you complete the SRS, you have to define the SIL target for the individual SIFs. You need to make sure there is some safety margin there. And this is what it looks like again in Excellencia. See the frequency targets. So let's now go to our Excellencia demo. Now, can we all see this Excellencia demo? There should be a page with the demo up. Can somebody send me a, just to make sure? We had a little problem. Can we see this okay? Okay, so now we're in Excellencia. And let's come here to the dashboard. Normally, we have a dashboard that gives you an overview of the system that you have. And here you can see we have number of units defined as 1, number of hazards per unit we have 3, and so we're showing that we have the SIL target distribution of 1 and 2. We haven't achieved our SIL distribution because right now we haven't done our design. We're just going through doing our selection. Once we've done our selection and the SRS has been completed and the design done, then you can go back and do the SIL verification. So over here on the left we have the project information, but also you'll note here we have project options. Now, I mentioned earlier that Excellencia covers the full safety life cycle, so we have a PHA tool, we have our SILect tool for SIL selection, we have an SRS tool, we have a SIL verification tool, and we have a life cycle cost calculator. Since we're only looking at SIL selection, we've just got the SILect tool. So up here on the right hand side, you'll see we have SIF identification and SILect. If we go to SIF identification, here we're showing the name, which I've called SIF01, and it's the Excellencia demo. Description is SIL Select demo. But the hazard that it's protecting against is overpressure in the boiler. The consequence description here is boiler rupture and explosion. So you can create a SIF entry and put in the parameters and the hazard that you're trying to mitigate against. So here I have 3 SIFs entered. We come over to the right hand side here. We have the SIF information. You'll see it says edit. If you click the drop down, it says edit, review, closed, rejected, or not applicable. What this enables you to do is you can do your SIL selection, and then you could submit it for review. Once it's been reviewed, if there are no more edits, you can close it. And when you close it, as we'll demonstrate in a minute, you will not be able to make any further changes. The other thing you can do is you can add team members. So if you've got team members, you can add them. We have Dave B. We can add Dave B. He's the Mechanical Integrity Manager. So we put him and he appears here. His role was not defined. You can define the roles. So you can have facilitator, you could have scribe, you could have participant, you could have expert, whatever description or role you have. You can add references. So if you have reference documents, reference information, you can add those there. And any actions. So if, as you're going through doing the design or even, the determination or even the review, you can allocate actions. So, and this pane at the top gives you different views. So here, these are overviews. Here are the details. So you can see, okay, we have a SIF01, we have 2 SIF01s. So let's change this one and say this is SIF03. And we have the SIL Select demo, overpressure in the boiler, boiler rupture and explosion. And the target is set for 2 for this one, set for 2 for this one, and set for 1 for this one. Now, as we go through, it's very important to make sure that you've done some calibration on your tools. If we go to the SIL Select tool, you can see here we have 3 basic SIFs using different techniques. So we have frequency, we have risk graph, we have hazard matrix. If we come over here, you can see here are the types of methods used, and the one highlighted is the one that we have here, risk graph. Same thing again in terms of your editing. You have all the session information. You can add the team members again. So if we double click our risk graph, you can see here now we have the information available for us to review and modify. If you come over and double click on the risk graph here, you'll actually see the risk graph. And you'll notice down here you can either use the VDI VDE 2180 risk graph or the standard risk graph that comes up in default, and this is the one that's in the standard. By loading defaults, Excellencia has defaults loaded, but you would calibrate these based upon your company's risk tolerance criteria. And over here we see we are using risk graph. We're looking at personnel at the moment. If you click on the options button, you can see now we have the personnel consequences, so we have those defined here. You have asset loss, so you have, these can be, again, depending upon your criteria, what these numbers are. You have your demand rate, so you have 3. You can actually extend that to 5. And in the new Excellencia 4 that's going to be released in Q3 this year, there won't be any limit on the number of these. But right now we have 3 shown for demand rate, environmental loss, and custom. So custom, you might say, all right, let's have one here for, click on custom. Let's have one here for business impact. And then you define what that would be. Then presence in the danger zone, seldom to frequently, frequently to continuous, probability to avoid hazard under certain circumstances, or almost impossible. Those are the ones that we saw earlier. So we can click OK on that. And here you'll see we have a little consequence description. So you can click on that and it tells you, okay, what's this SIF trying to protect against? Okay, boiler eruption, that's the consequence, boiler eruption and explosion. And you can, as you can see, you can put comments down the side here. And if we look, independent layers of protection. So we've said, all right, we have a pressure release valve and we have an operator alarm. So based on the criteria we've selected here, low to 1 to 10 years, seldom to frequently, probability to avoid almost impossible, personnel safety, several deaths, environmental impact, large uncontained release, and asset damage of 1 million to 6 million with 5 to 15 days, and a business impact, we come up with personnel safety of SIL 1, environmental SIL 2, and asset SIL 1. So the dominating factor here is the environment, and therefore we get a target of SIL 2. And as I mentioned earlier, this depends upon how you have calibrated your risk graph. So if we go then and look at our hazard matrix, here we have our relief valve as our independent layer of protection. Same thing again, you can double click on the hazard matrix and it'll bring up the hazard matrix. You can see here, there are the demand frequencies. We're covering personnel, environmental, assets, and custom, and we have our business impact there. These would be calibrated according to your risk tolerance. And as I mentioned earlier, when you start up, it loads with the defaults. And over here is a little description that explains how selecting the hazard matrix option allows you to calibrate the hazard matrix. So, as I mentioned earlier, you can do your calibration, which is important, because if you don't, you're going to get different results from the tool. And if you click the drop downs here, we've said demand rate greater than 500 years, 100 to 500 years, 20 to 100 years, 4 to 20 years, and 0.5 to 4. If you said 0.5 to 4, you can see now our SIL has changed. It's gone to a SIL 2. So we could also add in here another layer of protection. Let's say here we wanted to put an operator alarm. So there will be an alarm, the operator would take action. For that, the credit we can take is 0.1. So it means 90% of the time the operator will perform the task. And this is per the standard. So if you pop that in, you now see we've managed to get us back to a SIL 1. So IPLs will have an impact. You can also add comments. So any notes or comments you want to make, and you can build up several layers, independent layers of protection if you have them. You can put comments in here. Here we've said localized effect, but if you were to say, all right, there was a major effect on the environmental, now you've pushed it back up to SIL 2. And then if we go to our frequency based, so again, double click this, it brings up the frequency based targets, which you would then have to calibrate based upon your risk tolerance criteria. And this would then drive the results coming from this tool. So here we're saying multiple fatalities, major effect, major cost. We could say there was a business impact that is, let's say, local. And what's our initiating event? In this case, we're saying that our control loop fails. And we have here some IPLs, we have our relief valve, we have our operator action. Let's move this up a bit. And you can see the unmitigated frequencies are shown here for each of the particular categories. We've said our frequency of failure is 0.001 per year, so it's a pretty low failure rate. We didn't have any enabling conditions. And we're looking down here then at our tolerable risk frequencies from our table, the sum of our unmitigated risk frequencies, and therefore what would the risk reduction factor be. And we're seeing here, again, we're looking at a SIL 1, but this is recommending a SIL 2. So the safety margin that's been put in is to say SIL 2. Because this is pretty low, it'll be a low SIL 1, which again could mean that you will end up with a design that is still not safe enough. So it's always better to err on the conservative side as opposed to being too optimistic. Now we can say here, if we come over here and say, we've done the review and we've closed it. Then you have to enter why are you changing the status of the tool. You can say review, complete, and accepted. And you click OK, and now you have an audit trail. And you'll notice now that these are grayed out, so you cannot change them. So now this SIF has a SIL 2 determined. And that's what would be then used when you go to use the SRS tool. The beauty of Excellencia is that as you build up your design, you can move from one stage to the next in the life cycle. And with Excellencia 4 that we have coming out, like I said, in the end of Q2, early Q3, that has more integration. We have a LOPA tool, we have our PHA tool, and they all integrate into the SILect and the SRS and the SIL verification. So it's very easy to use. And as you can see, we've used the three main types here. It makes a very nice audit trail too, because you can keep track of what was done, what was changed. You can see here our session, this was one session, there could be multiple sessions. You can document each of those sessions. You can record the members and include references and documents that you need to refer to. So if we go back to our dashboard, we can see here now our target SIL distribution for all of three is now SIL 2. We've evaluated all the hazards. We haven't done any design yet, so that's showing a 0. So this is just a useful thing. And you can see here that we haven't done our SIL distribution, so we don't have anything yet to see in terms of SIL verification. So I see that there are some questions. Let me have a look here. Let me see what these questions are. There's a couple of questions here that have come in. One is, can I import from other systems in terms of list of safety functions from, say, PHA? Well, Excellencia does have an import capability. You can import CSV or text files, and those can be taken in and then used in the SIL Select tool. And can things be customized? Well, yes, hopefully you saw that we can customize. There's a lot of customization you can do. You can change colors and various other things. And that's very important. And there's a question that's come in that has 3 parts. I will probably have to answer that question because it's quite detailed. For example, what should be done if it's classified as a SIL based on a risk graph? Risk graphs, and I said, as long as you're consistent in the technique you're using and you're conservative, you shouldn't have too many problems. The important thing is to make sure that you do err on the side of caution. We do have in Excellencia, there's a SIL threshold. You might have seen that can be set that says, okay, if I have a low, for example, it's a SIL threshold of 1, so if I have a low SIL 1, then the SIL threshold will kick me up into SIL 2. That way it'll be safe, because if you have a low SIL 1, you may end up with an under-design. Whereas if you have a SIL 2, the designer, and you haven't put a risk reduction factor, the designer will most likely design towards the lower end of a SIL 2. That's just the way that things tend to happen. So it's always better to err on the safe side. And when you come to do the actual SIS design, Excellencia does have embedded in it the database of failure rates. So you can, when you're building your SIF, and next week's webinar is going to be doing SIL selection using Excellencia, and we will look there at how you can use that manufacturer's database that we have with specific manufacturers' devices and model numbers that have been certified to either SIL 1, SIL 2 or SIL 3, along with logic solvers. So you can create a SIF which, as you know, consists of a sensor, a logic solver and a final element. You can create your SIF using SIL rated equipment. Excellencia allows you to choose non-SIL rated equipment, and you can do proven in use. It also allows you to use your own failure rate data. But there's always a word of caution with that, to make sure that the failure rate information you've got is good, because the taxonomy of data is one of the most important things in getting good failure rate data. Not using cycle test data for example, what we call demand in 61511 or low demand in 61508 applications, because there you're looking at a demand of less than once a year. So most of the time your final elements will be static. They won't be moving. So cycle test data doesn't apply in those instances, because number one, they're continuously moving. Number two, they don't have the environmental conditions, because these tests are done in labs. And number three, you don't have product moving through them. So you could have dirty product moving through them that would have different problems for the particular final element device. And you don't check for stiction, which is something that happens. So that's very important to recognize. And of course, testing is very important. Proof testing is something that is also taken into consideration when doing the SIL calculations using Excellencia. So that's just a word of warning. Be careful. Make sure when you do your SIL selection that you do err on the conservative side. Obviously you don't want to over-design because it becomes too expensive, but you need to make sure that if you do decide, okay, I am going to go with a risk reduction factor of 20, so I will go with a SIL 1 with a risk reduction factor of 20, okay, fine, but just be aware that that's a conscious decision to do that. You can, as I was saying earlier, you can choose to, if you do end up with a risk reduction factor of 20 from using the frequency-based method, you may say, well, I'm going to specify I want double that, or to be safe, I'll say a risk reduction factor of 60. So I want a SIL 1 still, but I want a risk reduction factor of 60. So that gives you your safety margin. Any more questions? I don't see any more questions at the moment. There's one more couple of questions coming. Let me just have a look. One of the questions is, audio is no longer working. Can you all hear me still? I would hope you could hear me. Let me go back to the